We are going to see the next problem. So that is design a sequential circuit for the state diagram shown in the figure. Use state assignment rule. They're asking us to use the state assignment rules for assigning the states. So in the previous problems, we have assigned the states randomly. So we have given the binary values randomly, but here we have to use the state assignment rules. So unless mentioned, you should not go for this state assignment rules. You do the problem normally if it is not specified. If it is specified, use state assignment rule, then you have to do by the state assignment rules only. So this is the given state diagram. When you are in state A, when you are providing the input 0, it is going to state B, the output is 0. Similarly, you are in state A, you are providing the input 1, it is going to state C and the output is 0. Similarly, you are in state B, when you are providing input 1, it is going to E, and you are in state B, when you are providing input 0, it is going to D, output is 0. Similarly, you are in state C, when you are providing input 0, it is going to E and output is 0. When you are providing the input 1 from C, it is going to D and output is 0. Then you are in uh, similarly for the states D and E. So next what we are going to do is we are going for the state table from this state diagram. Similar to the previous problems, we are getting the state table from the state diagram. So this is the state table what we got from this state diagram. Here also we have to check for equivalent state. So by verifying this, the next state are same, but the output is not same. So here is no equivalent states. So there is no way for state reduction. So now checking for equivalent states. So we have verified the table. There is no equivalent states. So there is no way for reduction. So next one is assigning values to the states. So we have to assign the values to the states depending upon the state assignment rules. So since there is no state reduction in this problem, we can use the same state diagram what that is given in the question for checking the rules. So if there is state reduction, then after state reduction, again you have to draw the state diagram, then you have to check for that rules. Now, rule 1. So what rule 1 is saying is the states having the same next states. The states having the same next states for a given input condition should have assignments which can be grouped into logical adjacent cells in KMF. So you consider two, two states having the same next states. The states, if you're having two states, if that two states having the same next state, then that two states has to be and has to be in the logical adjacent cells in the K map. So that is in simple we can say this rule 1 is nothing but uh, you remember like this many to 1. Rule 1 is if many states having one state as the next state, then these states should be assigned in the nearer cells of K map. So again I will tell once more this what this rule is saying. The states which are having the same next states or given for a given input condition should have assignment which should be grouped into logically adjacent cells in the K map. You just remind one thing many to one. So now we will go to the state diagram and I will clearly explain what the rule is. Now we are going to apply rule 1. So I am taking the state A. I am taking the state A. The rule 1 is saying that states which are having the same next state, the states which are having the same next state for a given input condition should have must be placed in the neighboring cells in K map. So you take A. So you consider A for states. So you consider A. For A, the inputs are coming from D and E. So the next states of E and D are A. So once again, I am telling first you consider state A. Now you have to check from where A is getting the inputs. So A is getting the inputs from D and E. So D and E should be placed in the nearer cells of K map. Okay. Now we can go to B. You consider B. B is receiving input only from A. It is receiving input only from A. So rule 1 can't be applied to state B. Now you come to C. C is receiving input only from A. Here also the rule will not apply. Now you come to D. You come to state D. D is receiving input from C and D. In C and B. In other words, by the rule I will tell the states B and C have D as the next state. So B and C should be placed in the nearer cells of K map. So while considering A, this D and E, they should be placed in the nearer cell. When considering this D, C and B should be placed in the nearer cells of K map. Now you come to E. E is also getting input from B and C. So B and C should be placed in the nearer cells of K map. So rule 1 completed. From rule 1, what we understand is the states D and E should be placed nearer cells in the K map. Similarly, the states B and C should be placed nearer cells. So by applying the rule to the state diagram, we got that D and E should be in the nearer cells and B and C should be in the nearer cells. Okay. Now we are going for rule 2. So what rule 2 is saying is states which are the next states of a single state should have assignment which can be grouped into logically adjacent cells in. Here you remember one thing, one to many. So from one state, if the next states are two different states, that two different states should be placed in the adjacent cells in K map. So we will go to the, now we are going to apply rule 2 to this state diagram. So you consider state A. From A, the next states are C and B. So B and C should be placed in the nearer cells of K map. Similarly, you take B. From B, the next states are E and D. So E and D should be placed in the nearer cells of K map. Now you go to C. C, E and D or the next should be placed nearer cells in the K map. Now you go to D. From D, it is going only to one state A. So rule 2 cannot be applied to state D. So E also it is only going to A. So rule 2 cannot be applied. So we have applied rule 1 and rule 2. Rule 1 is from where a particular state is getting inputs. Rule 2 from a state which are the next states. Rule 1 is if A is a state, then from which are the states A is a next state. Rule 2 from A which are the next states. So we have applied rule 1 and rule 2 and we have got some conditions. So here totally we are having 5 states. To represent 5, we need 3 variables, minimum 3 variables, and we have to draw a 3 variable. We have to draw a 3 variable k map. So since we are having uh, we need 3 bits to represent 5, we need 3 variables. So we draw a 3 variable map, and by applying rule 1 and 2, we understand that the B and C should be in the nearer cells of K map. Similarly, D and E should be in the nearer cells of K map. And you can write A anywhere in this K map. Okay, but writing nearer is better. So from this K map, we have to take the value. The value of A is 0, 0, 0, and value of B is 0, 0, 1, and value of C is 0, 1, 1, and value of D is 1, 0, 1, and value of E is 1, 1, 1. So from this K map, we got the values of A, B, C and A, B, C, D and E. Next, similar to the previous problems, we have to go for the transition. We have to go for the transition table, and here we are using T flip-flop. So after filling that transition table, here you are having uh, 3 variables for present state, or 3 variables you have used for the states. So you need 3 flip-flop. So we have used T flip-flop here. So advantage of T flip-flop for the filling this value of TA, TB and TC flip-flop inputs. So for that we have to check A and A1 0, 0. So you have to put 0 here. Then 0, 0. So you have to put 0 here. 0, 1, 1. For T flip flop, for 0, 1 and 1, 0, we have to put 1. Next, we will be comparing A with 0. Again, 0, 1. 0, 1 is 1. Again, 0, 1, 1. Similarly, we have to fill all the things. Then here you are having four inputs A, B, C, and X, and we have not used all the 15 combination. For unused state, you have to put don't chaos. Then you have to draw K map for TA, TB, TC, and output. So since you are having 4 variable, you have to draw 4 variable K maps. First one is for TA. You have to check the column of TA, then you have to plot ones, zeros, ones and don't chaos. Then you have to put don't chaos for unused state. After that, you have to group and you have to find the expression. Then for TB, similarly, you have to check, you have to group and you have to write the expression. And for TC, you have to group and you have to write the expression. Finally, for output, you have to write the expression, you have to plot, group, and you have to write the expression. Then you have to implement by using T flip-flop. Okay, this is the implementation. So you have to draw 3 T flip-flops. T flip-flop is having only one output, and output of first one is A, and second one is B, and third one is C. Then this is the input X, and this is X, and this is X bar. And similarly, you are having the expressions for TA, TB, and TC, and depending upon that, you have to give the connections. Okay, so we have completed the third problem. Okay, so these 3 models you are having by using state diagram. You have to derive the state table and state reduction, then state assignment, then transition table, then finding the number of flip-flop, then uh, after that you finding the expression for flip-flop inputs and outputs, then implementation. This is the way for doing this problem in sequential synchronous sequential circuit design problems. We are going to see the analysis of sequential circuit. So the steps for the analysis of sequential circuit is, first we have to determine the flip-flop input equation and output equation from the sequential circuit. So from the given sequential circuit, we have to determine the flip-flop input equation and output equation. Then we have to derive the transition equation. Then We have to plot the next step map for each flip-flop. For each flip-flop, we have to plot the next step map. Then we have to plot the transition table. Then finally we have to draw the next we have to draw the state table, and finally we have to go for the state diagram. So the steps are, first step is we have to determine the flip-flop input equation and output equation from the given sequential circuit. Then we have to derive the uh, transition equation. Then you have to plot the next step map for each flip flop. Then we have to plot the transition table. Then you have to draw the state table. Then you have to draw the state diagram. So next we are going to see a problem. So in the problem, so a sequential circuit has two JK flip flops A and B. So how many JK flip flops we are having? We are having two JK flip flops A and B with two inputs X and Y. We are having two inputs and two JK flip flops and one output. The flip flop functions and the circuit output functions are as follows. So here in this problem, instead of giving that sequential circuit, they have given the input and output functions of the flip-flop input functions and output functions. And they are asking us to derive first the logic diagram, second the state table, third the next state equation for A and B, and the fourth one is we have to derive the state diagram. So in this given question, instead of giving the circuit, they have directly given the input flip-flop input functions and output functions, and they are asking us to draw the logic diagram, and they are asking us to draw the derive the state table, next state equations and state diagram. So the type of flip-flop what you're having is JK flip-flop. In some other problem you can get SR flip-flop or some other D flip-flop or T flip-flop. Here the type of flip-flop is JK, and we are having two flip-flops A and B and two inputs X and Y. So first, by using this given flip-flop input functions and output functions, we are going to draw the logic diagram. So this is the logic diagram. So you are having two flip-flop JA and JB, and you are having two inputs X and Y, and you are having one output. You are having one output Z. So you are having one output Z, and the Z also we have to draw here. Then we are having uh, one output Z. So first we have drawn the logic diagram. So next thing is we have to find the next state equation. So here this is a characteristics equation or next state equation of JK flip-flop. So Q of n plus 1 is equal to J into Qn bar plus K bar into Qn. So this is the next state equation or characteristic equation of JK flip-flop. Here you are having two flip-flops, one is A and another one is B. So we are modifying this to A and B. One for A, another one for B. Then first we are modifying it to A, and in the place of J we have put JA, and in the place of K we have put KA, in the place of QN we have put as NA, and uh, we have put as NA. Now from the question they have given the value of JA, KA and QN. A bar is nothing but A bar, QN of A is nothing but A. Okay, this is the outputs of flip-flop. Next, we are substituting this value of JA, KA, then QNA bar, QNA in equation 1. So we will be getting equation 2. First, we are writing the characteristic equation of JK flip-flop. Here you are having two flip-flops, one is A and B. So you are modifying that as A. You are putting the suffix as A, and we are writing the value of J and K from the question, and you are getting the equation number 2. Next, here you are having two external variables X and Y and two state variables A and B. So here next step is we want in order to find the next state map, we need to draw a map having four variables. That is, you have to draw a map with four variables. A, B are the state variables, and X and Y are the external inputs. So you must write like this. First you have to write the state variables, then only you have to write the external variables. Okay. So similarly, now we are taking the first cell. For example, you take the first cell. So in the first cell, the value of A is 0, value of B is 0, value of this is the next next state map of A. This is nothing but next state map of A. Next state map of A. So this is a next state map of next state map of A. So this is a four variable K map because we are having two state variables and two um, external inputs. Here we are not going for mapping and grouping. We want to find the values of the cells. So first we are taking the first cell, that is this is 0 0 0 0. So the value of A is 0, value of B is 0, value of X is 0, and value of Y is 0. And we are substituting in the equation 2. So this is equation 2. In this equation, we are substituting A is equal to 0, B is equal to 0, X is equal to 0, Y is equal to 0. So B is 0, X is 0, B bar is, that is 0 bar, Y bar 0 bar, then A bar 0 bar, then B bar 0 bar, then X 0, Y bar 0 bar, then 0. Next 0 into 0 is 0, then 0 bar is 1, again 0 bar is 1, then that 0 bar is 1. Then here also 0 bar 1, then 0, then 0 bar 1, then into 0 they are having a whole bar. Here 1 into 1 is 1, here 1 into 0 into 1 is 0. So you will be getting 0 plus 1 into 1. And here 1 into 0 into 1 is 0. So 0 bar into 0. Next is 0 plus 1 is 1. Then 1 into 1. Then 1 into 0 is 0. So we'll be getting 1 plus 0. So you'll be getting 1. So you have to put the first value of first cell as 1. Similarly, you are taking the fourth cell of first row. You are taking the fourth cell of first row. So the fourth cell of first row is the fourth cell of first row. This is the first cell of first row. Already we have got the answer as 1. The fourth cell of first row, value of A is 0, B is 0, X is 1, and Y is 0. So we are taking the fourth cell of first row, value of A is 0. So value of A is 0, value of B is 0, X is 1, Y is 0. So we are substituting in the equation 2. So in this equation you are substituting only X is 1, all the others are 0. So 0, 1, 0 bar, 0 bar, again 0 bar. Here also you are substituting. Then you are getting 0 into 1 is 0. 0 bar is 1. 0 bar is 1. So 1 into 1 is 1. Here also 0 bar 1. Here 1 into 1 into 1 bar. 1 bar is 0. So here 0 plus 1. Again 1. 1 bar is 0 into 0. So finally we will be getting 1 plus 0, 1. So the first cell, fourth row. Here also you are getting 1. Similarly, for each cell, you have to take the values and you have to substitute in the equation 2 and you have to find the next state map of A. Similarly, now we are coming for B. So q of n plus 1 of b. So in the next state equation of JK flip flop, we have substituted, instead of J, you have substituted JB, and instead of QN, you have substituted QNB, and here also instead of K, you put KB. And from the question, they have given the value of JB and KB. You are substituting in this equation 3, and you are getting the equation 4. Okay, now yeah, next we have to take a similar next four next map next state map for B. So this is the next state map for B. Okay, in this map we are considering the second cell of third row. Second cell of third row. In the third row, second cell we are taking. That is, value of A is 1, B is 1, X is 0, and Y is 0. And we are substituting the values in equation 4. These values we are substituting here. That is, here the value of A is 1. So 1 bar. X is 0. So 0. B is 1. So 1 bar. Here the value of A is 1. So 1. Then value of X is 0. Value of Y is 1. So 1 bar. Then the whole bar. So 1 bar is 0. So 0 into 0. Again 1 bar is 0. 0 into 0 is 0. 0 into 0 is 0. Here 1 plus 0 is 1. 1 bar is 0. 0 into 1 is 0. So you'll be getting 0. That is second cell of third row. Next we are considering third cell of third row. So first is second cell of third row. Then we are considering third cell of second row. The value of A is equal to 0, B is equal to 1, X is equal to 1, Y equal to 1, and we are getting the value as 1. So first we have considered second cell of, this is the second cell of third row. This is the third row. The value what is 0, correct. Then third cell of second row. Here got the value as 1. Similarly, we have to take each value and you have to substitute in the equation 4 and you have to find out these values. Then next we have to take it for output. So the output expression is Z is equal to AXY plus BX bar Y bar. Here also you are having 4 variables. You have to take the next step, next state map. So in the from the next state map, we are taking third cell of second row and we are substituting and we are getting it as 0. That is third cell of second row. Third cell of second row. We are getting 0. Okay, this is the next next state map for. This is the next state map for output. Output. Now, next what we are doing is we are combining the map of A and B, Qn of A and Qn of B. So we are combined and we have got like this, and this is the present state, and this is the input, and this is the next state. So from this we are going to form the transition table first. Then we are converting the transition table to state table. After forming the state table, we will be going for state diagram. Okay. So we have converted that the individual next state map to one single map. From that we can usually find the present state, input, next state. And you are having another map for output, that also we can take. So after combining these two maps, so we can form the transition table from this next state map. So next state, we have combined the next state maps of A and B, and we are having another map for output. By using these three maps or these two maps, we can now we combine this to one. So this one map and another output map, we can form the transition table. So this is the present state. If you take this as present state, 0 0 as present state, you take AB present state. If you are giving the input 0 0, the next state is 1 0. Similarly, we are giving the present state 0 0. You are giving the input to 0 1. The next state is 0 0. You are in the present state 0 0. You are giving the input 1 1. It is going to the next state. It is going to the next state 0 1. Similarly, you are in the present state 0 0. You are giving the input 1 0. It is going to 1 1. Similarly, you are in the present state 0 1. You are giving the input 0 0. The next state is 0 1. You are in the present state 0 1. You are giving the input 0 1. It is going to the next state 0 1. Then you are in the present state 0 1. You are providing the input 1 1. The next state is 1 1. You are providing the present state 0 1. You are providing the input 1 0. The next state is 1 0. Similarly, we have to form the next state transition table from this state table. So this is the transition table. So this, you are having the input, you are having the, you are in the present state 0 0. You are providing the input 0 0, and you are going to the next state 1 0, and output is 0. So you are having a output map. From that output map, you are writing the output also. Okay. So from here, you are writing the present state, then you are writing the input, then you are writing the next state, then you are writing the output. Then next step is we have to form a state table. Here you are having the state 0 0 0 1 1 1 and 1 0. So for 0 0, you'll be taking it as A. So next is conversion of transition table to state table. For 0 0, you are taking it as A. For 0 1, you are B. 0 1 0 for C, and 1 1 for D. So after that, you are, instead of that binary values, you are writing the states. So from this state table, you are going to draw the state diagram. So this is the state diagram you are drawing from that state table. So very easy. This is A. When you are providing the input 0 1, it is in the same state A, and the output is 0. Similarly, you are in state A. When you are providing the input 1 1, it is going to state B. The output is 0. You are in state A. When you are providing the input 0 0, it is going to D. The output is 0. You are in state A. When you are providing the input 1 0, it is going to the state C, and the output is 0. Similarly, you have to draw it for all the things. So this is state diagram. So we have completed the problem. So this is the analysis of clocked sequential circuit or synchronous sequential circuit or finite state machines. Okay, this is the analysis problem. In some problem, instead of directly giving the flip-flop input and output equations, they will be giving the diagram. From that diagram, we have to derive the input equations, then we have to do the same thing. Okay, this is the problem. Construct the transition table, state table, and state diagram for the Moore sequential circuit given below. So this is the circuit given, and we have to find the state table, transition table, and the state diagram for the given circuit. So this problem is an analysis problem. This is a second model. The first model we have studied is they have given the equation, flip-flop input equations and output equations. From that, we have drawn the logic diagram, and we have found out the next state equations. Then that transition table, state table, and state diagram. But here they have given the logic diagram, and we have to find the flip-flop input and output equations. From that, we have to find the next state equations of the flip-flop. Then we have to find the next state table, then state diagram and state table and the state diagram. Okay, here the number of flip-flops is 2 flip-flops. Here having 2 flip-flops, and the type of flip-flops both are JK flip-flops. Okay, and you are having only one external input X. You're having only one external input X, and you are having two flip-flops J and JA and JB. Okay. So you're having two states, A and B, two states, and one external variable X. And this circuit's output is independent of the external input. It is only depend on the uh, states of the flip-flop, that is A and B, that is output of the flip-flop. So the circuit is nothing called Moore circuit. So the output is depending upon the input and present state, then it is more melee. But here the circuit, this F is only depending on A and B. A XOR B is nothing but your F. So the circuit is a Moore circuit. So first we have to find the input J. What is J? J is nothing but B. J is nothing but B. Now that is JA. KA is nothing but X bar B. So X bar B, you are giving to AND gate, output will be getting X bar B. So similarly, JB is nothing but X bar. K is nothing but X XOR X XOR A. X XOR A is nothing but your KB. So from, and then output F is equal to A XOR B. So from this circuit, we have to find these things. That is, JA is equal to B, KA is equal to XOR B, X bar B, JB is equal to X bar, and KB is equal to X XOR A. Similarly, output Z or F. Output is F. F is nothing but A XOR B. Okay. Output is nothing but F XOR, sorry, F is equal to A XOR B. Okay. Next, then the type of flip flop is nothing but it is a JK flip flop. So we have to write the characteristic equation of JK flip flop. So the characteristic equation of JK or next state, other name of characteristic equation is next state equation. Next state equation of JK flip flop is Q of n plus 1 is equal to J into Q n bar plus K bar Q1. This is nothing but the next state equation of JK flip flop. Now here we are having two flip flops. One is A and another one is B. So for the flip flop A, we are giving the suffix A. So we are getting Qn plus 1 of A is equal to Ja into Qna of bar plus Ka bar into Qn of A. Okay. Then from question, we know that Ja is equal to B and Ka is equal to X bar B. And you are substituting this in this equation. And you know that Qn of A bar is equal to A bar, Qn of A is equal to A. So we are substituting in this equation. In the place of Ja, you are putting B, and in the place of Qn A bar, you are putting A bar. In the place of Ka, you are putting X bar B, and in the place of Qn of A, A. Okay. So we have got the equation 2. Equation 2 is we have got by substituting the value of Ja and Ka. Okay. So here we are having one external variable X and two state variables A and B. So you are having only one external variable X and two state variables A and B. So you have to go for a three variable map. Okay. So what you have to go? You have to get, go for a three variable map. Since you are having three variables X, A and B, you have to go for a three variable map. Okay. Now, similarly, we are going for JB. So the next state equation of B is nothing but Qn of B is equal to JB Qn B the whole bar plus KB bar Qn B. So from the question, JB is equal to X bar and KB is equal to X XR A, and Qn B bar is B bar and Qn of B is B. So we are substituting in equation 3 and we are getting like this. Okay. So now we have found out the next state equations for A and B. Now we have to consider a three variable map. So we have to consider a three variable map. Okay, I will show. you consider the three variable map. This is a three variable map for A. Okay. So this is a three variable map. So the here the variables are A, B and X. Okay. Now first we are coming to A. So we are considering the second cell of second row. So we are considering the second cell of this is the second row. Okay, we are considering the second cell of second row. Here the value of A is 0, B is 1 and X is 1. Okay, this is X. So A is 0, B is 1 and X is 1. And we are so we are considering the second cell of second row. So A is 0, B is 1 and X is 1. And we are substituting in this equation. B is 1. So we are substituting 1. A bar, A is 0. So 0 bar. Okay, then X is 1. So 1 bar. B is 1, 1. Then again A is 0. That is 1, 0 bar is 1. Then 1 bar is 0. Then here 0. Then 0 into 1 is 0. So 0 bar, 1 into 1 is 1 and 0 into 1 is 0. So 0 bar into 0. 0 bar is 1. 1 into 0 is 0. So 1 plus 0 is 1. So the second cell of second row, we have got it as 1. Okay. Now we will check whether that is correct. So we are getting 1. Similarly, you have to consider each row. Starting from here, you have to take 0, 0, 0 and you substitute in that equation and you have to write the value what you are getting. You will be getting 0. Then you have to take 0, 0, 1. When you are considering this cell, you have to take 0, 0, 1. Please listen, in this analysis problem, we are not going for grouping and finding the expressions. We are just taking the K map. Okay, we are taking the considering the map and we are finding the values of each cells and we are filling the cell. That is the only thing. So similarly, I have for an example, I have taken only this cell. Okay, similarly, you take another cell and you find you have to consider each and every cell and you have to find the value. Okay, now similarly, you have to go for B. For B, we have considered second cell of third row. Second cell of third row. Okay. Now we have that value is 1, 1, 1, and while substituting, you have got 1. Now you check second cell of third row for B. This is B. Second cell of third. This is the third row. First row, second row, third row. This is the second cell of third row. You are getting 1. Okay. Similarly, we have to get all the values for this cell. Okay. You have to find each and every value. Now, next we are going for output. So, output is nothing but Z is equal to A XOR B. So, it is independent of X. So, no need to consider X. So, just you take A and B. So, you write the output. 0, 0 XOR is 0, 0, 1 XOR is 1, 1, 1 XOR is 0, 1, 0 XOR is 1. So, we have got this is the value for output. Okay. Now, next what we have to do means we have to compare the cells of A and B. This is B, this is A, and we have to compare these two. I will show. Now we have to compare these two. Now, while comparing, we will be getting like this. Okay, we'll be getting like this. From this, we have to write the state table. So, if you are considering 0, 0 as the present state, 0, 0 is the present state. And when you are giving input to 0, 0 is the input. We'll be getting 0, 1 as the next state. Okay. So we have to convert this table into transition table. Next is if you consider 0, 0 as the present state, if you are giving x as 1, that is input as 1, you'll be getting 0, 0. Similarly, if you are considering 0, 1 as the present state, and when you are considering x is 0, you are getting 2, 1, 1. When you are considering 0, 1 as the present state, when you are giving x is equal to 1, it will be going 1, 0. So we have converted that into this table. Table is nothing but transition table. So these are the states 0, 0. When you are providing 0, it is going to 0 1. Here output is independent of x, whether the x is having 0 or 1, you'll be getting 0. Okay, similarly for 0 1, output will be same, either the input is 0 or 1, the outputs will be same. Okay, so we have converted that this combined next state tables of A and B into a transition table. Next, we will be converting this transition table into state table. For that, we will be taking for A, we will be taking 0, A equal to 0, 0. Then B is equal to 0, 1. C is equal to 1, 1. And D is equal to 1, 0. So instead of this binary values, we will be giving alphabets. It is nothing called your state table. So this is a state table. So here A is equal to 0, 0, B is equal to 0, 1, C is equal to 1, 1, and D is equal to 1, 0. Okay. So replacing the binary values by alphabets, we'll be getting state table. So next what we are doing is we are converting this state table into state diagram. Okay. So this is a state diagram. So since the output of the circuit is independent of the external input, the circuit is nothing but a Mealy circuit, a Moore circuit. So in Moore circuit, you have to write the output inside the circle. So clear. So in Moore circuit, you have to write the output inside the circle. So this is nothing but the state diagram. Okay, this is the state diagram. This is the state diagram, and this is state diagram, and we have written the output inside the table because this is Moore circuit. This is Moore circuit. If it is Mealy circuit, you have to put a dash here and you have to write the output if it is a Mealy. But this is a Moore circuit. So we have written the output inside that state circle. Okay. So today we are going to see the topic counters in unit 3. In unit 3, we are going to see the topic counters. Now, what is counter? So, a counter will be having a group of flip-flops connected together to perform counting operations. So, usually group of flip-flop will be calling it as register. Okay. So, counter is a register or a group of flip-flop connected together to perform counting operations. It will count the input clock pulses. The counter will count the input clock pulses. That is number of clock pulses which is coming into the input. It will count. The number of flip-flop used and the way in which they are connected determine the number of states. So the number of states of the counter is determined by the number of flip-flop used and the way in which they are connected. Two broad categories. There are two broad categories of counters. One is asynchronous counter or ripple counter, and the second one is synchronous counter. So there are two broad categories. One is asynchronous counter, another one is synchronous counter. Another name of asynchronous counter is ripple counter. Asynchronous counter is also called as ripple counter. So in asynchronous counter, they don't have fixed time relationship with each other. In asynchronous counter, they are not having fixed time relationship with each other. Triggering does not occur at the same time. That is, we will not be providing the clock to all the flip-flop at the same time. So in asynchronous counter, we will not be providing the clocks at the same time. So they do not have a common clock pulse. This asynchronous counter or ripple counter is not having a common clock pulse. First, we are going to see a 2-bit. This is the diagram of 2-bit asynchronous 2-bit asynchronous So first one is asynchronous, 2-bit asynchronous binary counter. Binary counter means it will count from 0, 1, 2, 3, again 0, 0, then again it repeats. So this is binary count, 2-bit asynchronous binary counter. So the term asynchronous means you are not giving the clock to all the flip-flops at the same time. You are giving clock directly to the first flip-flop, and then for the second one you are taking the output, the complement output of the previous stage to the next stage. So you're not giving the clock, you are giving the clock directly to the first one, and for the second one and for successive ones, you will be taking the inverted input of the previous stage, and you are giving to the and giving us clock to the next stage. Okay, so this is the diagram. So then what your the type of flip flop you used for this counter is JK flip flop. So this is JK flip flop you have used. You have used two flip flops. So for 2 bits you are using two flip flops, and you are made both J and K of both the flip flops high. So what are the things we have done? First one is you made you used two flip flops. First one. Second one, since it is asynchronous counter, you have given clock directly to the first one, and for the second one you have taken the output, inverted input of the first one, and you have connected to the second one. So here the you do not have a common clock, and the triggering will not occur at the same time. Okay, then you have made that uh, the J and K inputs of both of the flip flops high. Now we are going, this is the clock. So clock is nothing but the square wave. Now we are giving in, we are going for the working. So since we are giving clock directly to the first flip flop, for ever, this is a positive edge triggered flip flop. So there are the triggering is nothing but changing the state, making the flip-flop to change its state is called triggering. So there are two types of triggering. One is edge triggering and next one is level triggering. There are two types of triggering. So please listen. This is a clock. So these are the two edges of clock. This is positive edge and this is negative edge. So there are two edges and this is level. So these are the two edges and this is level. So there are two types of triggering, that is edge triggering and level triggering. Edge triggering means making the flip-flop to change its states at this edges. This is positive edge and this is negative edge. If you are making the flip-flop to change its state at the positive edge, it is called positive edge triggered flip-flop. And if you are making the flip-flop to change its states at negative edge, then it is called negative edge triggered flip-flop. Now this is level. If you are making the flip-flop to change its state at this level, then it is called a level triggered flip-flop. So this flip-flop is a positive edge triggered. Our flip-flop is nothing but a positive edge triggered flip-flop. So this is the positive edge. So since you are connecting the clock directly to this first flip-flop, the first flip-flop will change during every positive edge. During every positive edge of the clock, this output of your first flip-flop will change. So we are going for the uh, working. The initially the output of both the flip-flops are 0. Okay, so output of both flip-flops. So we are going for the working. So initially both the flip-flops are 0. So if you are having 0 here, actually here you will be getting 1. So since we have put an inverter, that 1 will become 0 here. So this is a negative edge, positive edge triggered flip flop. This flip flop will will change its state only if you are having 1 at this place. Once again, I am telling you know that both the inputs, both the outputs of the flip flops are complement of each other. So if you are having 0 here, you will be getting 1. But since you have introduced an inverter or a bubble, that 1 will gets inverted and will be getting 0. So whenever you are having 0 here, it will not conduct this second flip flop. When you are having an output of 0 here in the Q naught, this flip flop 1, this is flip flop 0 and flip flop 1. The flip flop will not conduct. So only if you are having the 1 at the Q naught, then here it will be getting 0. That 0 will be inverted to 1. Then this flip flop 1 will conduct. Okay. Now I am going for the working. Initially both the outputs are 0. So you are applying at that time. Here you are having 0. That's 1. That 1 has inverted to 0. So it will not work. This second flip flop, that is f of 1, will not work. So initially both the outputs are 0. Now you are applying clock. It will become 1. But at that time here you will be having 0. So this flip flop will not work. So same output you will be getting here. You are applying the next positive edge. During the next positive edge, this 1 will become uh, 0 here. But at the time here, if you are having 1 here also, you are having 1. This flip flop work and this 0 will change to 1. Why? Because when in a JK flip flop, if both J and K are 1, the output will complement. Okay. Now your output is 0 1. Now again you are applying clock. This 1 will become, the 0 will become 1. At that time, the output what you are having here, that is in this place you will be having 0. So this flip flop will not work. So you'll be the same output you'll be getting at this place. Okay. So you'll be getting 1 1. Next, during next clock pulse, this 1 will become 0. So at that time he'll be having 1 here. So this flip flop also work. So this will again change to 1. So you are getting 0 0 0 1 1 0 1 1. Again it is repeating. The sequence is repeating. Again I will explain once more. So the second flip flop will conduct only when you are having an output of 0 here. Okay. Make the first point. Now initially both the inputs are 0. And this first flip flop f naught will change the state during every positive clock edge. This is the first positive clock edge, this is the second, this is the third, and this is the fourth. During the first positive clock edge, this will change to 1. But at that time this flip flop will not work. Why? Because here we'll be having 0. Since it is positive clock edge, the for 0 input it will not work. So we'll be getting the same output. Now, during the second clock pulse, this 1 will change to 0. At that time, what we're having is 1. So this flip flop will work. So this 0 will change to 1. So this is a JK flip flop, and both the inputs are made high. So for every clock pulse, it will toggle. Next, during the third clock pulse, this 0 will change to 1. But at that time, the value what we're having is here is 0. So the same output will be coming in the flip flop 1. Again you are during the fourth clock pulse, this 1 will change to 0. At that time the value what you are having is 1 here. So this 1 will also change to 0. So again the sequence is repeating 0 0 1 0 0 1 1 1 0 0. This is the working of asynchronous 2-bit ripple counter. So the same diagram. Here you are applying the main clock pulse only to the f of naught. So already I have explained. You are giving the main clock pulse only to the f of naught. The clock for the next flip flop is taken from the previous complemented output. So from here you are giving the clock. So all inputs J and K are made high. So this is a timing diagram. So this is your clock. First positive edge, second positive edge, third positive edge, and fourth positive edge. So this is Q naught bar. This is Q naught bar. So initially we are assuming Q naught and Q1 as 0. We are assuming Q naught and mm, Q naught and Q1 as 0. Okay. Now please listen. During the first clock edge, this is Q naught. It will change its state during every clock pulse because you are directly connected to the clock. So during the every, this is the first clock pulse. It is changing from 0 to 1. So during the next positive edge, it is changing to 0. It is again changing to positive, again changing to negative. So this is Q naught will change its state during every positive edge. So now you come to Q1. So first, after drawing this Q naught, you draw Q naught bar. So Q naught bar is nothing but the just reverse of Q naught. So if you are having 0 here, you are having 1. So if you are having 1 here, 0, then you draw Q naught bar. Now your Q1 will conduct only if we are having Q naught bar is